freely available on either the Moodle or the RCDMS platforms for your perusal at a later stage. And lastly, and more importantly, the feedback survey would be sent during the session. I would be posting it in the chat box. And the reason why we would require or would ask you to fill out the feedback survey is because we like to understand if this workshop was helpful and going forward, how we here at RCD can improve our offerings to support postgraduate students. It also ensures that you receive a certificate of attendance. So that will be posted shortly in the chat. So before we dive in today's session, I just want to introduce our speaker or our facilitator. Dr. Salami. She is a postdoctoral research fellow in the Department of Mathematics, Science and Technology Education at the University of Johannesburg, South Africa. She's also a lecturer in the Mathematics Education Unit, Department of Science Education at the Federal University in Nigeria. She holds a PhD and bachelor's degree in mathematics education from the University of Ilron, Nigeria. I hope I'm pronouncing that right. And Dr. Salami's research focuses on effective constructs in technology enhanced mathematics, teaching and learning, curriculum development, instructional strategies, and gender related issues in mathematics education. Additionally, she is actively engaged in teaching research and academic development initiatives across Africa and internationally. So, without further ado, I'd like to hand over to Dr. Salami.
Thank you. I'm trying to share my screen.
Okay, yes, I can see it.
Yeah. Good morning, everyone.
Morning. Sorry, Dr. Salami. Just put it on presentation mode.
Yeah, thank you.
Okay, there we go. Perfect. Okay. Dr. Salami, are you okay there?
Yeah.
All right.
Yeah. Yes. Am I audible?
Yes, I can hear you.
Yeah.
Can people give a thumbs up just to confirm? All right.
Good morning, everyone. Thank you for joining today's session on statistical analysis basic concepts organized under the Research Capacity Development Management System at the Postgraduate School, University of Johannesburg, South Africa. My name is Olajumoke Olayemi Salami, and I am delighted to facilitate this important session that serves as a foundational pillar for your research journey. I'm a postdoctoral research fellow under the supervision of Professor Erica Doretia in the Department of mathematics, science, and technology education. The objective of this session is to understand key concepts in descriptive and inferential statistics, to recognize the importance of statistics in the research process, and to apply basic statistical techniques to analyze and interpret research data, and also to identify appropriate tools and approaches for handling data in your research. Yeah. What is statistics in research? Statistics in research is the branch of study that involves collecting, analyzing, interpreting, and presenting data in order to derive meaningful insights and make informed decisions. Statistics in research plays a foundational role in the research process by ensuring that findings are not only systematically obtained, but also logically valid and applicable beyond the specific sample studied. The use of statistics allows researchers to understand patterns, to test hypotheses, assess relationships between variables, and draw conclusions that can be generalized to broader populations. I'm considering this morning the statistical research and the basic concepts. We can see that statistics is not just a tool used at the end of a research study to analyze data. Statistics is a guiding framework that informs every stage of the research process, from designing the study to drawing conclusions. Statistics provides the structure that transforms raw data into evidence-based knowledge. And without it, research would lack the rigor and clarity necessary to advance understanding in any specific discipline. Being not giving the definition of statistics, what is statistical analysis? Statistical analysis is the process of examining data through the particular application of statistical methods to uncover patterns, relationships, trends, and insights. And it is a it is a core statistical analysis. This begins once data has been collected before any formal analysis is conducted. The data must undergo preparation, which includes cleaning, that is removing error or inconsistencies, organizing, that is structuring the data in a usable format, and verifying the data, that is making it more complete and reliable. And this foundation step is crucial because the quality of the analysis directly depends on the quality of the data. And statistical analysis is a dynamic rigor process that transforms data into evidence. It supports
Dr.
researchers in,
Salami,
yeah.
sorry. The slides are not moving on our side.
Yes, this slide we move. I'm trying to give the definition, the basic
Okay.
definition of statistics analysis, and the basic concepts. I'm speaking
Okay.
to the, yeah, yes,
Okay,
yeah,
thank you.
this,
Thank you.
yeah, yeah, you are welcome. So I've given the definition of the statistical analysis as the dynamic and rigorous process that transforms data into evidence. And being basic concepts, there are different basic concepts in statistics. Basic concepts in statistics form a foundation for understanding and conducting any form of data analysis in research. These concepts are deeply interwoven and serve as language through which researchers describe, interpret, and make decisions based on the data. And also understanding for anyone looking to make sense of numerical information, apply it in meaningfully in a research context. So there are importance of statistics in research, different importance in statistics in research. The first importance of statistics in research is to organize and summarize data meaningfully, because statistics is a language of research and it enables a researcher to organize and summarize data meaningfully. What do I mean by organizes and summarizes of data in a meaningfully way? This is a central task in the research process that transform raw information into a structured and interpretable form. When a data is first collected, it often exists in a disorganized and overwhelming state, making it difficult to extract insights on detect pattern. The process of organizing data involves arranging it in a logical order and classifying it according to relevant variables, and whereby structuring it in a way that facilitates further analysis. And summarizing data, on the other hand, involves condensing the bulk of information into a manageable form that highlights the key characteristics and differences without distorting the underlying facts. And also, on the summarizing data typically follows a process of organization, and the goal to provide a snapshot that reflects the main features of this data set without requiring someone to examine each individual data point. So this is where statistical techniques like calculating averages, medians, proportions, and measures of spread come into play. So, for example, rather than listing the score of every student, a researcher may report that the average scores was 75, which is standard deviation of 10. So, where immediate conveys both the typical performance and how much variation there was more among the scores. And also, the essence of organizing and summarizing data meaningfully is not a technical task. It is an art of interpretation, structure, and clarity. And organizing and summarizing data meaningfully enables the transition from raw, unreadable data to insight, from coerce to comprehension, laying the groundwork for valid and impact research outcomes. And another importance of statistics in research is to draw conclusion from a sample and generalize to our population. And drawing conclusion from a sample and generalizing to a population is a fundamental objective of inferential statistics in research. This allows researchers to study a manageable subset of a larger group and then reasoned assumption or prediction about the entire group based on the subset, which is also known as the sample. This process is essential because in most cases it is impractical, costly, or impossible to collect data from every member of a population. So the underlying logical is based on the promise that a careful selected sample, and this is ideally choosing from random or systematic sampling techniques, and which can reflect the characteristics of the larger population with a known level of accuracy. So a sample serves as a representation of the population, and when statistics methods are applied appropriately, researchers can estimate population parameters such as means, proportions, or correlations based on sample statistics. And another importance of statistics in research is identifying patterns, relationships, and trends in data. So identifying patterns, relationship, and trends in data is a core objective in of statistics analysis, and is central on to make sense of information collected during research. And the process is involved examining the data carefully to discover recurring themes, consistent association or changes over time that can provide insight into the underlying phenomena. And the patterns in data typically refers to repeated or predictable arrangement that emerge when data is organized and visualized. And I have on the slide here another importance is the test of of hypotheses and guides of decision, of informed decisions. So the test hypothesis and making informed decision is a central aspect of the scientific research process rooted in the principle of statistical reasoning. The process begins with the foundation of competing hypotheses, the null hypothesis and the alternative hypothesis. The null hypothesis is typically represents a position of no effect, no difference or no relationship, and it acts as the default assumption that is tested against. So while the alternative hypothesis reflect researchers' actual belief or suspicions, and often the presence of an effect when there is effect or difference that the research aim to detect. So the goal to assess whether the evidence in the sample is strong enough to reject the null hypothesis in favor of the alternative hypothesis. And the last importance is to enhance research credibility and rigor. This is when the findings is this is when an essential this is an essential aspect of scholar work by ensuring the results are not only valid but reliable, but also trustworthy and meaningful with both academic and practical context. When the data collection process must be transparent and objective, minimizing bias or any distortion. So in qualitative research, this may involve using standardized tools and protocol, while in qualitative research, it may require careful documentation of researcher perspective and procedure. So without the statistics, when data is presented without interpretation, it remains a collection of raw numbers, and these raw numbers are unrefined and ultimately unhelpful. So simply listing statistics or qualitative findings without drawing meaning from them render research inert. It makes it useless. So this absence of interpretation means decision makers are left without direction. So they may see trends or anomalies but have no clarity to on these causes or significance. So without statistics, data is just raw numbers and there will be no clear or direction, and the research becomes speculative and lacks grounding. What is statistical thinking? Statistical thinking involves approaching problems with critical reasoning. Statistical thinking that involves critical reasoning is a disciplined and structured way of approaching problems by actively analyzing, questioning, and interpreting data rather than accepting information on just a face level. It is not merely about applying mathematical formulas or statistical processes. Critical thinking is about using logical context and also evidence to assess the data truly reveals, what it might obscure, and how confidently conclusions can be drawn. And when we talk about statistical thinking, it's working with uncertainty and variations. And when a data is uncertainty, the statistical thinking with willingness to work with uncertainty and variation is an acknowledgement that data, especially when drawn from real world context, is rarely exact or deterministic. In fact, instead of seeking absolute answer or perfect prediction, this mindset embraces the reality and that variability is inherent in any process or population, that the uncertainty is a natural process of decision making based on the data. And uncertainty arises from the fact that we often work with samples rather than entire populations. So no matter how careful selected a sample cannot perfectly represent every feature of a population. And this sampling variability means the different samples from the sample population can yield different results. So statistical tools such as confidence interval and probability distribution are specifically designed to account for this uncertainty. So, and providing a framework for making informed conclusions. So a researcher who accepts uncertainty does not claim uh, definitive truth based on one result. Instead, they describe findings in terms of probabilities, likelihoods, and margins of the error. So when we talk about variation similar refers to the differences observed in data. That is differences between individual group, time periods, or measurements. And a willingness to work with uncertainty and variation is what distinguishes statistical thinking from simplistic and deterministic reasoning. And it reflects a mature understanding of the complexity of the world and a commitment to evidence-based conclusion that respect the complexity. So by acknowledging what is not known as careful as what is known, researchers and decision makers can act responsibly, minimize error, and build knowledge that is both nuanced and reliable. So we divide statistics into two branches. There are two branches of statistics. The first one is descriptive statistics and inferential statistics. Descriptive statistics is a method that involves summarizing and organizing data. For example, the measure of central tendencies, which are averages. The averages are the mean, median, and the mode, and measures of spread, which is range, variance, and standard deviation, and data visualization, which is the charts and the graphs. So descriptive statistics is a fundamental branch of statistics that focus on methods for summarizing, analyzing, and presenting data clearly and informative. So rather than making prediction on or drawing conclusions beyond the data at hand, descriptive statistics aim to provide an accurate picture of what the data reveals within its specific context. And the process of descriptive statistics transform raw data, often complex and unstructured. So it transforms data into a meaningful form that can be easily interpreted and communicated. So one of the primary tasks of descriptive statistics is to convey the central location of the typical measure within a database. And when a data is skewed or contains outlier, the median may be a more representative indicator than the mean. So in addition to identify central tendencies, descriptive statistics also examines how data is spread and dispersed. So understanding the spread is critically because two databases can have the same average, but differ widely in terms of variability. So measure of dispersion, such as the range, variance, and standard deviation, described how the individual data points deviate from the average or from each other. So a smaller spread suggests the data points are closely clustered around the central value, so indicating consistency or uniformity, whereas a larger spread reflects more variability or unpredictability within the data base. So in essence, descriptive statistics provide the foundational tools needed to explore. It describe from the word descriptive. It make sense of data. So descriptive statistics form the initial stage of analysis, setting the stage from more advanced techniques while also offering valuable insights on their own. So through descriptive statistics, researchers can gain a clear understanding of their data set structure. Researchers can also prepare for further analysis, and they can communicate findings in a coherent and accessible way. This helps us describe what is going on in our database. And the second branch of the second branches of statistics is inferential statistics. Inferential statistics made prediction. It generalized about a population based on a sample. Differential statistics includes hypothesis testing, confidence intervals, and regression analysis. Inferential statistics also allow us to answer questions. It allows us to answer key questions in like, is the observed difference statistical significant? Can this result be generalized to the wider population? These are the questions that are key questions in inferential statistics. What is the probability of the error? So each inferential statistics is also a branch of statistical science devoted to drawing conclusions from a broader population when only a subset of that population, that is the sample of the population has been observed, because observing every member of a population is usually impractical, as I've said before. Researchers rely on probability theory to quantify how much trust can be placed in statements and extend beyond the data in hand. So all inferential procedure rests on the three pillars. And the first pillar is a well-designed sampling strategy to obtain data that represents the target population, a mathematical model that links the sample to the population, and a framework for quantifying uncertainty so that conclusions carry explicit statements about their possible errors. So the first task of inferential inference is estimation. So estimation is where unknown population parameters such as means, proportions, or regressions, coefficients, and approximated using sample statistics. So when the point estimates provide single it provides a single value best guess. And to acknowledge this, the researchers report confidence intervals that ranges calculated under repeated sampling. And when the goal is to evaluate a claim, so this is rather than merely estimate a parameter. So when we talk about regression analysis, extend inferential principles by modeling relationships. So we have discussed about the key questions in inferential statistics. The next slide is to understanding the data distribution. The first one is the normal distribution. When we talk about the normal distribution, this is the distribution that linked it link is the distribution that link probability and sample together. So a distribution is a way of mapping all the possible values of a variable. And this can be done how frequently each occurs. So the normal distribution, for example, is a theoretical model that describes how data tends to cluster along the mean in many nature phenomena. So when data is collected repeatedly through random sampling, the sampling distribution is the sample mean that tends to approximate a normal distribution. So this and there is a something that is named in statistics that is the central limit theorem. So the principle is also is what allow researchers to make statistical inferences, to estimate population parameters, to construct confidence intervals, and also to conduct hypothesis testing. The normal distribution is the symmetrical bell shaped curve. Is the symmetrical bell shaped curve, and it's also the scale distribution is the asymmetric is asymmetrical, and the data leans left or right. And the skewness affects the interpretation of the mean and the median. So probability and sampling overview. Probability and sampling overview. This section introduces us to the foundation concept of probability and sample. Probability and sampling form the essential foundation of inferential statistics. This enable researchers to move beyond simply describing data toward making meaningful conclusion and broad population. So sampling comes into play because it's really feasible or even possible to collect data from an entire population. So instead, researchers gather data from a subset or a sample and use probability theory to infer characteristics of the whole population. So the quality and method of sampling they are critical here. They are critical here. So a well choosing random sample ensures that every member of the population has an equal chance of being included. So reducing bias and increasing the reliability of the inferences drawn. So the poor or non-randomized sampling, on the other hand, can distort results, and this can lead to incorrect generalization. So distribution link probability and sampling together. So a distribution is a way of mapping all the possible value and a variable that can take and how frequent each occurs. So the foundation for inferential statistics. So this helps to estimate likelihood and draw conclusions from the sample. And the key concepts like probability, samples, and the distributions. So there are basic probability concepts. Probability concept. The first basic probability concept is these are essential for understanding how uncertainty is measured and how likely outcomes are determined in any statistical analysis. So probability itself refers to a likelihood and a particular event that will occur, and this is expressed on a scale from 0 to 1. So a probability of 0 means the event is impossible, while a probability of 1 indicates it indicates certainty, that is possibility, and the values between 0 and 1 represent varying degree of likelihood. For example, the probability of flipping heads on a fair coin is 0.5, and since there are two equal likely outcomes, so to fully grasp how probability works, it's important to understand a few foundational terms. That is an experiment in any process or actions that results in an observable outcome, like flipping of a coin, rolling a die, and also conducting a survey. So an outcome is the result of a single trial of a experiment, and such as rolling a tree on a six-sided die. That is on a six-sided die. An event is a set of one or more outcomes. For instance, when rolling an even numbers like 2, 4, or 6. So it's an even composed of a multiple outcomes. So when we talk about independent events, are those whose outcome do not affect one another. They do not affect one another. And also, we have the population and the sample. Population and sample. Population is an entire group of interest. In research, we often cannot study an entire population, so we work with a sample. So it's very crucial to understand the difference. So there are differences between population and a sample. Population is the total number of like for instance, the total number of schools in entire community. So population, the differences between population and a sample is central to all statistical reasoning. So particularly in the context of inferential statistics, population refers to the entire group that a researcher is interested in studying. So it could be all registered voters in a country, every product coming off a factory line, or all patients with particular medical conditions. So population contains all the data points that would ideally be examined to answer a research question fully and accurately. So studying our entire population is often impractical. It is very time consuming and is expensive. So that's where a sample comes in. So a smaller, a manageable subset of the population that is actually observed and analyzed. So sampling allows researchers to conduct study more efficiently and very effectively, while still gaining insight. And for example, instead of surveying every single consumer, a company might gather opinion from a few thousands and use statistical techniques to estimate the preference of the broader market. So while the sample is the practical tool for conducting research, the population remains the ultimate focus. So the power of statistics lie in its ability to take findings from a limited group, and through careful designed sampling and analysis, extend them to the much larger population with confidence and clarity. So why sampling matters? Why sampling matters? Sampling matters because it saves time. It saves time and cost. It makes data collection more feasible, and it allows the statistical inference when sampling is properly done. So there are goals. The goal to ensure the sample accurately reflects on the population. So another point is the random sampling and sampling bias. So random sampling is a fundamental technique in research design that ensure every number of the population has an equal chance of being selected for the sample. So it's a method of essential the random sampling is essential because it minimizes the influence of external factors and personal judgment on the selection process. So when random sampling is properly implemented, it increases the chances that the sample will be representative of the entire population. And when in turn strengthens the validity and generalizability in the research findings. So sampling bias undermines the trustworthiness of a research. So it is a picture, it is a distort picture of population, and this can be, it can failed intervention. Yeah. And to guide against this, researchers use randomization and clearly defined inclusion and exclusion criteria. So randomization ensures that the selection process does not favor any particular individual or subgroup. So while clear criteria maintain it helps to maintain consistency and transparency in who is eligible to be part of the sample. So together these practices help to eliminate hidden patterns that could compromise objectivity. And this allows the study to reflect the broader reliability and in which it aims to understand. So, and ultimately, the credibility of any research project rests not only on the data collection, but on how it was collected. So random sampling and the deliberate avoidance of bias are what make the difference between trustworthy insights and statistic illusion. And there is another concept in statistical research, in statistical analysis, is the central limit theorem, that is CLTM. CLTM is a cornerstone of inferential statistics. It is one of the most important and powerful principles in statistics because it explains why the normal distribution appears. so frequent in data analysis. And it states the sample, how the sample size increases, the sampling distribution of the sample mean we tend to approximate a normal distribution. And also CLTM the implication of the theorem are profound. It provides the theoretical foundation for using normal based method in inferential statistics, and such confidence interval and hypothesis test. So when the population distribution is unknown or non-normal, CITM justifies the widespread use of the normal distribution and as a model of statistical inference, and it also underpins the accuracy of estimations derived from sample data. So CLT allow researchers to quantify the uncertainty of their estimates using the standard error of the mean. So which measures how much the sample mean is expected to vary the sample of the data. So in essence, CLTM bridges the gap between randomness of real-world data and the structured total of statistical analysis. And it shows how through aggregation and repetition randomness can yield, and it make it one of the cornerstone of modern statistics. And why CLT matters is because it justifies the use of the normal distribution in many statistical procedure, and it allows researchers to make inference about the population mean using sample data. And it also explains why larger sample needs to be more reliable estimate. So for example, if the random sample of test score of 30 students from different schools repeatedly, so the average of those sample will form a bell shaped, which is normal distribution. A normal distribution is in form of bell shape, and even if the individual scores are skewed, so the probability and sampling principle are essential in designing valid research. And it also makes sound inferences from data and avoid error in generalizing results. Then there is another concept, basic concept in statistical analysis is inferential statistics, which I've talked about before. I will still speak to it. That inferential statistics allow researchers to make conclusions about a population based on data collected from a sample. Yes, and descriptive statistics summarizes data. So under inferential statistics, we have hypothesis testing. The hypothesis testing is a formal procedure for evaluating ideas. Yes, it evaluates ideas about population using sample data. And the purpose is to determine whether the observed effect in a sample is strong enough to be generalized to the population, or whether it occurred by chance. And there are steps in hypothesis testing. The first step in hypothesis testing is to state the hypothesis, whether it is null and or alternative. The second step is to set the significance level, and the significant level is usually it is identified by alpha. And the third step is to choose the appropriate test statistic. Then you calculate the test statistic and p-value, making you make a decision whether to reject or to fail to reject the null hypothesis, whether to reject the null hypothesis or to accept the null hypothesis. And the second thing is the null and the alternative hypothesis. The null hypothesis assumes no effect. When there is no difference, it's the default. When there is no effect, when there is no difference, that is that is null hypothesis. And when an hypothesis is alternative, that is when it assumes that there is an effect and when there is a difference. So examples of a null hypothesis is when there is no difference in test scores between male and female students, when there is no difference between a collaborative based on the topic of the researcher. So when we are example of a null hypothesis is when there is no difference in the test score between male and female students, and the alternative hypothesis is when there is difference in the test score between male and female students. So the goal of hypothesis testing is often to determine whether to reject uh, the null hypothesis, which is H naught, in favor of the alternative hypothesis based on evidence from that data. Then there is what we call type 1 and type 2 errors. In hypothesis testing, understanding type 1 and type 2 error is crucial because they represent the two primary risks when making decision based on sample data. So the type 1 error denoted by alpha as indicated on the slide occurs when the null hypothesis is true, but we incorrectly reject it. So this is also known as a false positive. So concluding that an effect or difference exists when in reality. So it does not. So for example, if a new drug is no better than the existing one, but the test result lead us to wrong conclude it is superior. So we've committed a type 1 error. So the probability of making this error is controlled by significant level, typically set at 0.05, meaning that there is 0.05 that meaning that there is 5% risk of falsely detecting an effect, because 0.05 is the same thing as 5%, that is 5 over 100. On the other hand, a type 2 error denoted by beta occurs when the null hypothesis is false. You know, I said type 1 error is a false positive. So the type 2 error denoted by beta occurs when the null hypothesis is false and we fail to reject it. This is a false negative. The alpha, which is the type 1 error, is also known as false positive, but type 2 error is known as false negative. So missing an actual effect or difference. So using the same drug example, a type 2 error would mean this would mean concluding that the new drug is no better when it actually is. So this drug is more likely when sample size are small or the effect size is subtle. So the power of a test defined as 1 minus beta. So this reflects the probability of correctly detecting a true effect. So ultimately, both types of error, it highlights the inherent uncertainty in statistical inference and the importance of thoughtful experimental design, appropriate sample sizing, and careful interpretation of results. So another basic concept is in statistical analysis is p-values and significance level. What is p-value? When a p-value is it is a central concept in hypothesis testing. It represents the probability of obtaining the observed results or something more extreme. Assuming the null hypothesis is true, it quantifies how compatible your data is with the assumption that there is no real effect or difference. So a small p-value indicates it indicates that the observed result would be quite unlikely if the null hypothesis were true. So it provides evidence against alternative hypothesis. So to interpret the p-value, it is compared against a pre-established significance level. So commonly denoted by alpha, with 0.05 being a typical threshold. So this level represents the maximum probability researchers are willing to accept for making a type 1 error. That is, rejecting the null hypothesis when it is actually true. So if p-value is less than or equal to is 0.05, if it is less than or equal to alpha, if your alpha, that is 0.05, the result is considered statistically significant. Then, and the null hypothesis is rejected. So this suggests the observed outcome is unlikely to be due to random chance alone, and there may be a genuine effect present. So on the other hand, if the p-value is greater than 0.05, if your p-value is greater than your alpha, we fail to reject the null hypothesis, meaning there is not enough evidence to support a statistical significant difference or relationship. And this does not prove that the null hypothesis is true, only that the data doesn't provide strong enough grounds to conclude otherwise. So another start concept is confidence interval. Confidence interval is it gives a range of values. Yes, it gives a range of values within which we expect the true population parameter to lie. And this with a given level of confidence interval is usually 95, it is usually 95%. It's usually 95%. Example is if the average of a test score is 70% with a confidence interval of 95%. We are that is confidence interval of 68 and 72. 68 and 72. We are 95% confident that the population mean lies between 68 and 72. So why confidence interval is useful is because it indicates the precision of an estimate, and it provides more information than a single point estimate or p-value. So a confidence interval is a statistical range that calculates from sample data and is believed to contain the true population parameter, and such as the mean proportion. So which is with a certain level of confidence. So confidence interval provides more information than a single point estimate by expressing both the precision of the estimate and uncertainty inherent in the sample. So because of our time, I will not be able to give more examples under the confidence interval. On the slide, we have the introduction to t-test. T-test is also this is a common statistical test used to determine whether observed difference or relationship are statistically significant. So t-test is used when comparing means between groups. They are usually used when comparing means between groups. We have different types of t-test. There are one sample t-test. One sample t-test compares a sample mean to a known population mean. We have independent t-test, which compares means of two independent variables. For example, male and female students. Maybe positive attitude or negative attitude. And also we have a paired t-test. A paired t-test compares means from the same group at different times. For example, before and after and an intervention. So t-test is a fundamental statistical method used to determine whether there is a significant difference between means, and it helps researchers draw conclusions about population based on the sample data. It is especially useful when dealing with small sample sizes and when the population standard deviation is unknown. We use t-test. Then the common scenarios in real-world research. So t-test relies on the t-distribution, which resemble the normal distribution, but has heavier tails, allowing it to account for greater uncertainty in a smaller population. So there are three primary types of t-test. And I've talked about it, the one sample t-test, which compares the mean of a single sample to a known hypothesizing population mean. Then the independent t-test, which is also known as two sample t-test, which compares means of two separate unrelated groups. And the peer t-test, which are the same participant, which is which account for the natural correlation between paired observation and also improving statistical power by controlling for individual differences. So t-test is widely used across disciplines because of its simplicity and effectiveness in testing mean differences. So when its assumptions are met, it provides a robust way to determine whether observed patterns in sampling data are likely to reflect true differences in the population. And another basic concept used in statistical analysis is chi-square. So the use to test relationship between categorical variables. Chi-square test of independence assess whether two categorical variables are related. For instance, whether they are two categorical variables are related. So, and also to determine, okay, there is also, I have here with me the chi-square goodness of fit. Yes, the chi-square goodness of fit, it tests whether a sample distribution fits an expected distribution. So whether a sample distribution fits an expected distribution, that is what is referred to chi-square goodness of fit. The chi-square test is a versatile statistical tool used primarily to analyze categorical data, and it points the data points sorted into distinct groups or categories rather than measured on a continuous scale. So it helps researchers to determine whether there are meaningful relationships or differences between categorical variables like male and female students in education. So making it a staple in fields of social sciences, medicine, and marketing. So one common application is the test of independence, which examine whether two categorical variables are related or associated with each other. For example, a researcher might use a chi-square to investigate whether gender is related to voting preference by comparing observed frequencies, like actual counts in each category with expected frequencies. So the test evaluates whether any observed differences are due to chance or suggest a genuine association. So chi-square test offers a straightforward way to analyze relationships and patterns in categorical data, helping researchers move before mere description to statistical supported conclusion about association or fit with expected models. And another concept is correlation and regression. Correlation and regression are statistical techniques which are used to examine the relationship between two or more variables. Correlation and regression are fundamental statistical techniques used to explore and quantify relationship between variables. It helps researchers understand how variables interact and influence one another. So correlation specifically measures the strength and direction of the linear relationship. It measures it measures the strength and direction of the linear relationship between two variables. So its values ranges from -1 to +1. And -1, it indicates a perfect positive relationship, while +1 indicates a perfect positive relationship. -1 represents a perfect negative relationship, and 0 means there is no relationship. So correlation does not imply causation. It simply describes how closely two variables move together. So on the other hand, regression analysis goes a step further by modeling the relationship between independent, which is predictor, the independent variable, and the dependent variable. The dependent variable is the outcome, and the independent variable is the predictor. So the simple form of linear regression fits a line to the data, and this allow researchers not only to describe the relationship but also to predict outcome and assess the magnitude of influence one variable has on another. So regression provides estimates of the slope and intercept, indicating how much change on the dependent variable is expected with one unit change in the predictor. Scatter plot. Scatter plot is it is a visual representation of the relationship between two continuous variables, and each point represents a pair of values, which is x and y. So it is useful for identifying patterns, linear, non-linear, or when there is no relationship, and it helps to detect the clusters. So examples of plotting, an example is plotting study R against test scores. Why this R is represented by X and the test score is Y, to see if more hours is study associated with higher scores. So a scatter plot is simple but yet powerful visual tool using to examine the relationship between two continuous variables. So each point on the plot corresponding to a pair of values. So one of the x variable and one from the y variable. So plotted on a two-dimensional graph. So beyond assessing the nature of their strength of relationships, scatter plots serve as a diagnostic tool to check for data quality and inform appropriate analytical choices. So scatter plots provide an immediate glimpse into the data structure, and it also they are often one of steps in exploratory data analysis when studying continuous variables. And we have Pearson correlation coefficient. Is another basic concept when considering statistical analysis, and is usually represented by R. It is a measure that indicates the strength and direction of a linear relationship between two continuous variables. So Pearson correlation coefficient is usually denoted as R, as indicated on the slide. It is a statistical measure that quantifies both the strength and direction of a linear relationship between two continuous variables. So Pearson correlation coefficient, it produces a value range. The value ranges from -1, -1 to +1, +1. So where a value of +1 indicates a perfect positive linear relationship, and meaning that as one variable increases, the other increases proportionally. So while -1 indicates a perfect negative linear relationship, where one variable increases as the other decreases proportionally. So a value near 0 suggests there is no linear correlation between the variables. So as is indicated on the slide, you can see that +1 is perfect positive. At 0, there is no correlation, and at -1, there it indicates perfect negative. So interpreting the magnitude of Pearson it helps to understand how strongly the variables are related. So the values between 0.70 and 1.0 is they are considered to represent a strong relationship, and this indicates that changes in one variable are closely linked to changes in the other. So correlations between 0.30 and 0.69 suggest a moderate relationship where the association is noticeably between not very tight, and correlations in the range of 0.10 to 0.29 indicates a weak relationship, meaning the variables share more connection and but it's limited. So lastly, values around 0.00 imply no meaningful linear relationship. There is no correlation. It is important to remember that Pearson correlation specifically measures linear associations. Variables with strong nonlinear relationship might have a low Pearson despite being closely related in other ways. And additionally, correlation does not imply causation. So even a strong correlation does not mean one variable causes change in the other. So Pearson correlation remains a widely used, and it is measured for quick assessing the direction and strength of linear relationship in quantitative data. Introduction to simple linear regression. Simple linear regression is a foundational statistical technique used to model and understand the relationship between two variables. So one independent variable denoted as S and one dependent variable denoted as Y. Y is the dependent variable and X is denoted as the independent variable. This is the primary purpose is to predict the value of y based on x and to quantify how much y tends to change when x changes. So the model is expressed by the equation from the word linear, line. So it's an equation on a line format. That is, the model is we have y equal to a plus b x plus e. Here, a is the intercept representing the expected value of y when x is 0. B is the slope, and this indicates the expected change in y from for one each unit increase in x, and e is the error term, and this which will capture the variability in y that cannot be explained by x. So the randomness or noise in the data. There is what we call noise in the data. So for instance, for the slope is particularly important because it tells us the direction and the strength of the relationship. And a positive slope suggests that it suggests that x increases, y also increases. A negative slope, suggests that y decreases as s increases. Positive slope suggests that s increases while y also decreases. So the size of b indicates the magnitude of this effect. So regression works by finding the line of the best fit. So typically using the least scarce method. So when minimizing the sum of the square differences between the observed value of y, those predicted by the model, once the model is established, it can be used not only to make prediction but also to test hypotheses about the relationship between x and y. So simple linear regression offers a powerful it offers a powerful yet accessible way to explore and quantify how one variable influences another. So it makes it a foundational tool in both scientific research and data-driven decision making. Example is by predicting students' exam scores. That is why, based on their study time. So a practical example of simple linear regression is predicting a student test score, which is why, based on the number of hours they spend in study, that is X. And this is classic scenario where we suspect a positive relationship. And the more the time a student spends studying, the higher their expected test score. So to explore this, data are collected from a group of students, recording how many hours each studied, and the test score they received. So a regression line, that is the line of best fit, is then drawn through the data points using the equation. That is test score is equal to A plus B study time plus the error. So E is the error. So now here, A is the intercept, the expected, the the expected, sorry, I want to plug my system.
Dr. Salami, are you
Yeah.
okay?
Thank you, I'm fine.
All
So on
right.
the screen, you can see the equation. That's the test score, A plus B study time plus the error. So to explore this, here, A is the intercept. A is the intercept, the expected
So,
test score
Dr.
when the
Salami,
start,
sorry. Uh,
yeah,
you say we can see the equation. We're on Pearson's correlation coefficient
yeah.
slide.
That's the
Um, so I'm just seeing it's like measures strength and direction of linear relationship. Is that where the equation is? I can't see it.
Yes, the equation I have test score is equal to A plus B bracket study time close bracket plus E.
No, I can't see that.
Wow. Can you see the assumptions of linear regression?
No, I'm
Wow.
just seeing Pearson. There. Okay. Yeah. Yes.
Have you?
Yes.
Okay, you are fine. Are you seeing the screen?
Yes, I can see it now.
Okay. Yeah. Examples of simple linear regression. Are we on the same page?
Yes.
Good. Thank you. Yeah. The test score is equal to A plus B bracket study time close bracket plus E. Here, A is the intercept, the expected test score when the study time is zero, and B is the slope. That is how much the test score increases for each additional hour of the study. And for instance, if the resulting model is test score is equal to 50 plus 5, open bracket study time, then close the bracket. This means that a student who studies 0 hours is expected to score 50, and each additional hour of study increases their expected score by 5 points. So a student who studies for 4 hours is predicted to score 70. So after fitting the model, we assess the strength of the prediction using HARP scale. So these examples illustrate how simple linear regression not only helps visualize and understand the relationship between two variables, but also allows for quantitative prediction and decision making based on the real world data. Assumptions of linear regression. Simple linear regression relies on several key assumptions to ensure that its estimates, uh, predictions, and statistical inferences are valid and reliable. So linearity is for there are four core assumptions of linearity. Normality of residuals, then homoscedasticity, that is equal when there is equal variance, and independence of observations. Linearity means there is a straight line relationship between the independent variable x and the dependent variable y, from the word linear. Linear, something on a line, equation on a line. So these assumptions ensure that the regression model accurately capture how y changes as x changes. So if the relationship is non-linear, the linear regression model will misinterpret the data, and its predictions and slope estimates will be they will be flawed. And this assumptions is typically assessed by visually inspecting a scatter plot or the residual plot to check the curvature. So normality of residuals refers to the idea of the errors, that is residuals, the differences between the observed values and those predicted in the model. So when that means that the differences between the differences between the observed values and those predicted by the model are normally distributed. So this assumption is especially important for conducting valid hypothesis tests. So creating accurate confidence interval, it does not mean that the dependent or independent variable must be normally distributed, but only the residuals, that is histogram or a Q to Q plot of the residual is commonly used to check this assumption. And homoscedasticity, when there is equal variance or constant variance, means the variability of the residuals. When the variability of the residual remain the same across the values of the independent variables. So if the residuals form a funnel shape in the residual plot, this indicates there is equal variance, there is heteroscedasticity. So ensuring this homoscedasticity allows the model to assign appropriate weight to the parts of the data. Then there are common statistical tools that are used. Researchers have access to variety of software tools for conducting statistical analysis. So the choice of tools depends on the data complexity, and it depends on the research goals and the user experience. And the choice of the data depends on available resources. So a variety of statistical tools are available to perform data analysis, and the choice of the tool can significantly influence not only how data are analyzed, but also how efficiently results are produced and interpreted. And the first common statistical tools is shown on the screen as this is SPSS. Is one of the common tools with the statistical package for the social sciences, and is widely used in the social sciences and psychology for its user friendly, which require minimal programming. So it is well suited for standard statistical procedures. So SPSS such as statistical procedures such as t-test, ANOVA regression and descriptive statistics, and making it ideal for users who prioritize each to use over customizability. And the next one is R. R is a powerful open source statistical programming language too. It is favored by statisticians and researchers who need flexibility and the ability to write customs analysis. So R is an extensive library of package for almost any type of statistical or machine learning task. So, but it has a steeper learning curve compared to point and click software. And another thing is Excel. Excel is accessible and is a familiar tool, and it is very good, particularly for beginners and business users. So it provides a basic statistical functions and visualizations, and is useful for small data sets and straightforward analysis. So Excel statistical capabilities are limited and can be prone to error in more advanced analysis due to its manual. So, and we have JASP, that is Jeffrey's Amazing Statistics Program. It is a newer statistical tool. It is an open source tool designed for users who want the simplicity of SPSS, but with more transparency and modern statistical technique. So it also includes Bayesian analysis. It is a menu driven and it also produces publication ready output. And Python is a full-featured programming language widely used in data science. So Python can be handled. It can handle everything from data and visualization to modeling and machine learning. So it strengthens Python lies in its integration with broader software ecosystem and its suitability for automating and scaling analysis workflow. So depending the choice of the tool an individual want to use, the depth of statistical analysis require the user's programming experience and the need of automation for customization. So I have here with me a comparison of popular tools. So the slide shows the popular statistical tools that integrate their description strengths and their user interfaces. When choosing a statistical tool, the decision often depends on the complexity of your analysis, the user's background, and the specific goal of the project. For instance, like SPSS it is developed by IBM statistical tool, and it is well established software, particularly favored in the social sciences and education due to its intuitive point and click graphical user interface. So this SPSS offers a streamlined workflow for performing standard statistical tests, making it ideal for users with limited coding experiences and who still require robust analytic capabilities. And in R is an open source programming. It's an open source programming language and designed specifically for statistics and data visualization. And R flexibility and Power Library support a wide range of advanced, and this makes it is it makes popular among statisticians and researchers who need precision and control in their analysis. And Excel is why not built solely for statistical tasks? It remains a highly accessible spreadsheet tool that it supports basic statistical functions such as descriptive statistics, correlation, and regression. So its widespread use and familiar user interface make it a go-to choice for simple analysis or when quick. So visual summarizes are needed. And JASP represents a new generation of statistical tools. It is an open source of user-friendly. It is designed to lower the barrier to perform a rigorous statistical test, and with modern GUI and native support for both frequency and Bayesian method. JASP is particularly well designed for students, educators, and researchers looking for clarity and productability without the need to write code. And finally, Python is a general purpose programming language and is widely used in data science and machine learning. So with powerful statistical libraries like pandas and stats model, Python allows for end-to-end data workflow for cleaning the visualization to modeling and deployment. So there are user-friendly interfaces like SPSS and JASP, which are most approachable for beginners due to their graphical user interface. And Excel is widely known and great for basic statistical summarizes and summaries and visualization. R and Python are ideal for those with programming experiences or advanced statistical needs. When it comes to user-friendly interface, in statistic software, the level of accessibility varies widely depends on the tool design and intended audience. So Excel is also it is particularly for basic summaries, data entry, visualization such as charts and pivot tables. So when to use which tool? When to use which tool? Choosing the right statistical tool depends heavily on the research context, the type and the scale of data, and the goals of the analysis. So for basic analysis and descriptive statistics, such as calculating means, frequencies, or creating simple charts, Excel or SPSS is usually the best choice. Excel spreadsheet environment is intuitive for quick summaries, while SPSS offers structured procedures and clearer statistical reporting, especially for the users without coding experience. And in educational settings, JASP, that is Jeffrey's Amazing Statistics Program, or SPSS, is often recommended. Both have user-friendly graphical interfaces and guide users through common tests like t-test, ANOVA, and correlation. So JASP in particular is helpful for introducing Bayesian concepts in a non-intimidating way. When the analysis becomes advanced or requires customization, such as building a specialized model, writing repeatable scripts, or integrating multiple data sets, R or Python becomes more appropriate. These programming languages offer the flexibility to tailor every part of the workflow, and these are especially valuable in the fields that demand complex modeling and custom statistical models. And for automation and reproducibility research, especially when consistent, large scale analysis are needed, like R and Python are also preferred. So they support scripting, version control, and integrate with productivity framework like R Markdown or Jupyter notebooks. So which ensure analysis are transparent and repeatable. So if the goal is to conduct Bayesian analysis, which focus on updating probability based on prior knowledge and observed data. So JASP or R are ideal because JASP include built-in Bayesian option with simple controls. And while R offers powerful Bayesian packages like BRMS and RStan for deeper customization and modeling. So finally, when working with larger data sets or big data, tools must handle memorable, efficient, and scale well, like Python and R with libraries designed for handling large volumes of data and interfacing with databases and cloud computing are far more suitable than spreadsheet-based tools like Excel. So when which can become unstable or limited in such scenarios. So the decision about which tool to use should be driven by the complexity of the task. So the level of statistical or programming expertise and the need for precision, flexibility, and scalability. So there are resources for further learning, like books, discovering statistics using SPSS or Handy Field, practical statistics for data scientists by Peter Bruce and Andrew Bruce, online platforms, YouTube SPSS and Excel tutorials. So tools to practice Excel, built-in function JASP is free online App Studio. They are also free, and there are some institutional access of SPSS. Thank you for participating.
Thank you so much, Dr. Salami, for that insightful and comprehensive presentation. Really, really appreciate it here at the RCD, and I'm sure it's been just a wealth of knowledge for the attendees today. So thank you so much for sharing. I am now going to be opening up the floor for questions, comments, or suggestions. Or if you are unsure of something, I think now is your time to speak. You can raise your virtual hand or you can just type your question in the chat box. Dr. Gabriel.
Yes, Miss Andrea, can you hear me well?
Yes.
All right, thank you. Dr. Salami, thank you so much for a very comprehensive presentation. You took me back to
Thank you, Doc.
all the basics, some of the things that I have even forgotten about, so it just demonstrates the comprehensiveness of the presentation that you brought before us today and the depth of preparation that you also took into, preparing for facilitation of this workshop. I thank you so much for that, and even just for honoring us with accepting our invitation to facilitate the session for today.
Thank you, Doc.
Yeah.
You are welcome.
Thank you, Dr. Gabriel. All right. So does anybody have any questions? Or is there something that wasn't clear in the presentation and you need Dr. Salami to maybe go over it again? Okay. Laurent just put a comment in the chat. Oh, okay. It's fine. I'm just monitoring the chat on my side. I can't see any questions or comments just yet. So, Dr. Salami, I think that presentation was quite clear and comprehensive. Um, all right, anybody questions or suggestions? And Dr. Salami, from my side, how long have you been within the mathematics sort of discipline? How many years?
Thank you very much. I'm into mathematics education more than 10 years.
More
Yes,
than
as
10?
a,
Oh, wow.
yeah, more than 10 years.
Wow, wow. And what first drew you to mathematics? Because, mathematics is quite a difficult subject for most people.
Yes, you can repeat your question.
I'm saying, what was it that motivated or drew you towards mathematics? Because mathematics and mathematics education, it's quite difficult for most scholars to grasp, the concepts.
Yes, the reason why I study mathematics because it is a foundational and logical thinking and it's a problem solving. Mathematics help me to understand the world in a structure and precise way. It teaches patience, discipline, attention to detail, and whether it's solving real life problems. And also it develop new technologies. It make sense of data. Mathematics is always as the core and enjoy the challenge it presents and the satisfaction that comes from finding solution. And most importantly, studying mathematics open the door to many opportunities in science, education, engineering, and beyond. Thank you.
Thank you. Thank you so much for that. All right. Anybody? Questions, comments, anything you're unclear about? Okay. In the absence of questions or comments, Dr. Salami, we here at the RCD want to thank you for supporting us and thank you for your time and assistance. We really do appreciate it and appreciate you coming and facilitating the workshop here today. Um, okay, I see there is a question. You can go ahead. You can unmute your mic and go ahead.
Thank you so much for this workshop. I'm Babatunde Oladile. Dr. Salami, thank you for this comprehensive presentation. You have actually given us a kind of detailed statistical analysis. I really commend you for this presentation. I would like to add, what is the home of AI in terms of this statistical analysis? How can we actually a lot of AI tools now can actually do statistical analysis. So I want to ask, how can we actually leverage on the AI statistical proficiency? Thank you.
Thank you very much, Dr. Oladele. AI in statistical analysis, it refers to the use of machine learning and intelligent algorithms to enhance. And it uncover complex patterns. AI helps to make predictions and also handle large data sets more efficiently. So AI tools can detect missing data, errors, making pre-processing faster than more accurate. So AI helps in statistical analysis. It's one of the automated data cleaning preparation, and it helps to create model that predicts outcomes like customer behavior, maybe disease risk on patterns in data, and it also enable the analysis of textual data, for instance, like a survey or feedback. and this will, which is difficult to handle using standard statistic. So in a big data analysis with AI, statisticians can work with massive data sets, and these that are too large or complex for traditional tools. Thank you.
Thank you so much, Dr. Salami. I hope that answers you. Uh, is that okay? Okay, I'm assuming that. All right, perfect. Okay, any other questions or comments? Okay. All right. In the absence of questions and comments, I'm going to be drawing this workshop to a close. Again, Dr. Salami, thank you so much for your assistance, for your time and consideration, and more importantly, supporting the RCD. To all the attendees, thank you so much for taking the time and attending. We also really appreciate it. I just wanted to remind you that I have posted the feedback survey in the chat. Please ensure that you fill it out in order to get your attendance, your certificate of attendance for this workshop. There has been a question regarding how to access these recordings. As previously mentioned, these recordings will be uploaded on your Moodle platform and the RCDMS platform. It will be uploaded by the end of the week. So you can check in around Thursday, Friday, and it should be up for you to view. And yes, I think that's it from our side. I just want to say thank you, everybody, and have a lovely Monday further. And we wish to see you in future workshops. And Dr. Slami, is there anything you want to say in closing from your end?
Thank you very much. Thank you for giving me the opportunity to present and also to present. Thank you very much.
Thank you so much. All right. Have a lovely day further, everybody. Take care and keep warm. Bye bye.
Bye.